We had talked last time about the Uden-Wentworth grain size scale. And so what we're really talking about is detrital rocks and how we categorize them. And so we do it all by grain size when we talk about detrital sedimentary rocks. I'm going to show you some examples. And also one of the things that we like to keep in mind is that when we talk about detrital sedimentary rocks, we're talking about rocks that were weathered, have been removed by erosion in some way, and then were transported in some fashion. And then very commonly, they will end up, eventually in the ocean, some of them. Anyways, not all of them. Some of them will. If you want to, why don't we just take a little mini vacation? I'm gonna let you think about this for a minute. If you're up in the mountains and you can imagine a quiet landscape that is, a stream flowing through a valley. And when you look down in that valley, what you see down there are a whole bunch of giant boulders that have fallen from the edges of that canyon. And so they accumulate down at the bottom of that ravine, if you will, or that big, wide V-shaped valley that's down there, right? That's up in the mountains. Let's say it's in Colorado, in the Front Range, right? And so if that's the case, okay, so those rocks will accumulate down there at the bottom. And then every once in a while, you get these amazing flash floods that will blast through and wash a lot of those boulders a little bit farther downstream. And then eventually they're going to hit other boulders and they break into smaller rocks. And so what you get is a variety of different sizes. You may get things that are, 3 or 4 meters across, or you may get things that are, block size like so. And you may get sand grains even eventually in that, right? And so sand grains would be coming also from the weathering of sedimentary rocks up in the hills. And so if you can imagine that very dynamic and very energetic sort of like landscape, okay, in which you have that deep valley that has this accumulation of boulders, and every once in a while they get blasted out by these flash floods. And then also you get landslides. And so the landslides would deliver materials also from the valley walls. And eventually you get out to the front of the Front Range, and you get what we call alluvial fans out there. And so alluvial fans are accumulations of all that debris that was washed out of that canyon and a series of events, okay? And so there's one event after another, millions of years, okay? So after millions of years, there's a huge accumulation out in front. Now, you already know that when you go to the beaches, like if you go down to let's say Corpus Christi, or if you go down to the coastal beaches in Texas or Louisiana or Mississippi or even in parts in Florida, right? You don't find boulders at the beach unless they've been moved there, right? So people put boulders there to stop erosion, but that's the only, and they have to be brought in by man. They don't come in by, natural processes, right? And what do you find down there? Well, you find sand at the beach usually, right? Unless it's a very low energy beach, and then you might find some silt or something like that, right? But the waves come in and they wash the material around. And every once in a while, you may have a river that dumps material out there as well. Well, what's the river dumping out there? Well, a lot of muddy water, right? Those are clay grains, those are silt grains, and then maybe some very fine sand grains also, and that's like the Mississippi. So if we started in that canyon over here in Colorado, and we move downstream out of the canyon and into the plains. And so as we go farther and farther away from the mountains, there are fewer and fewer boulders there. In fact, what we usually see is gravel, right? So gravel and pebbles, granules, sand, and not too muddy except when it floods, right? And so you keep going downstream. And so let's say we're in Boulder in that area. And so if you follow the rivers a little bit farther downstream, a lot of those actually accumulate. Like there's the Poudre River, there's the St. Vrain, there's a whole bunch of other rivers that flow across that landscape. But eventually most of them converge and eventually flow into the Platte River. And so the South Platte River is very commonly associated with the detritus from the weathering of the Rocky Mountains. And so the detritus, that material that gets washed out of the Rocky Mountains, eventually, by the time you get to Nebraska or right near Nebraska, it's mostly sand grains when you get there. because all of the bigger pieces would have stopped already. It takes a lot of energy to carry pieces of gravel. And so, but not so much for a sand grain, because sand grains can roll, they can flip, they can hop, they can do all sorts of things in the water column. And as you follow it downstream, the Platte River eventually runs into the Missouri River. And you may have heard of the Missouri River as being the big muddy. And so when it gets down and the Platte River finally makes it into the Missouri River really muddy, but it has sand grains in it too. Those sand grains will wind up in sand bars along the edge of the valley there. And then eventually it gets finer and finer and finer as you go. But you still get the sand grains, but you don't get so much the gravel and things like that, right? No boulders at all. And eventually when you get down to Louisiana, it's nothing but the very fine sand, the silt, and the muds, right? So it's like you get the clay sized grains as well. So only the finest grains make it the farthest distance. So when you're up in the canyons, that's where the edges get knocked off of the boulders when they bang into one another, and nature doesn't like sharp edges, and so it tends to take those and round them a little bit. And in fact, that's one of the things that water erosion is really good at. It's able to round the corners off and actually make smaller pieces out of bigger pieces. And so if that's the story, if that's the vacation we just went on, all the way from the mountains all the way down to the beach, and the beach, of course, we have sand, and when you get farther offshore, it gets finer and finer grains, actually. So only at the shoreline do you get pretty nice rounded, sand grains, quartz grains perhaps, and then a little farther offshore where it's quieter water and you're below the wave base, you actually get silt deposited there, and a little farther out you may get some shale deposited, or clay grains, right? And so the very finest grains in the deepest, stillest water, because otherwise, you've probably shaken up dirty water before, and it takes a while for those really fine grains to fall out. The larger grains fall out much more rapidly. So that's what we have when we talk about detrital rocks. We have environments of deposition. Those could include river valleys. They could include the mouths of canyons. They could be in places like lakes. Okay, so lakes are another environment of deposition. Beaches, of course, offshore areas. In fact, even in the deep oceans, you can get submarine canyons, and submarine canyons very typically have submarine fans out in front of them. And then eventually, when you get to the very deepest parts of the ocean, only the very finest grains get deposited there. And so in the very, very deep oceans, you find that there's a very, very shortened sort of time frame for how grains get transported there. Sometimes they're wind blown and they hit the ocean and will settle out that way, but most of them are very fine grains. And so there are red clays in the deepest of the oceans, in fact. But it's a very slow history of sedimentation when you get into the deep oceans. For the rest of this, the sedimentation is pretty rapid. And so we're going to go into that, and we're going to talk about how you can have different kinds of sediment associated with each one of these different depositional environments. And so that's where we're going today. So Udden-Wentworth tells us that there are big grains and small grains. And in between, there are processes that sort those grains. So if grain size is the most important aspect of figuring out what kind of rock we have, whether it's a conglomerate or a breccia if they're not rounded, clasts, or sand grains. They could be coarse sand grains up to 2 millimeters in size, or they can be smaller than that. And they can be, you can have finer grains than even very fine sand, right? And so that's going to be the silt size. So that's 1/16, I think it is, of a millimeter. And then beyond that, you can get clays when it gets to the very, very finest grains, right? And so we have different rocks that we name after each one of those. So we have conglomerates and breccias at the upper end. We have sandstones where it's sand grains that are, it doesn't matter what they're made out of so much as it is more the grain size that's important. So sand could be anything practically. It could be a carbonate. It could be a silicate mineral of some sort. And then when it comes to silt too, but most commonly silt tends to be quartz grains, or quartz very fine, very fine grains, I guess you could say. And then clay minerals are, in fact, the weathering products of things like feldspars, pyroxenes, amphiboles, and the micas. And so that's what you get when you weather those sorts of materials, all derived from igneous rocks for the most part. Now, you can weather anything, but the things that we have in the oceans and different depositional environments, they can come from all over the place. What I like to say is that every rock tells a story. So in this photograph, stop talking so much now. In this photograph, you can see, here's Nancy again. She's standing in front of a pile of boulders, and those boulders, in fact, have a matrix around them, and that matrix, in fact, is made out of conglomerate. And the rock itself is a boulder conglomerate. Well, it's boulders at the bottom anyway, and at the very top, it tends to be smaller and smaller grains. Well, that's one of the things that we notice about detrital sedimentary rocks. They tend to have a sort of sorting, if you will, based on how they accumulate. And so in this case, the interpretation that we see for this, because we understand what happens in the modern depositional settings, because we can go out with a backhoe and dig a trench across an alluvial fan, and we can see that they're the same kind of rocks that you see in this image right here. And so that's an ancient rock, of course, but it accumulated originally at the mouth of a canyon as an alluvial fan. And so that is what we would regard as a conglomerate to begin with, but it has an environment of deposition, we like to say. And every rock tells a story. And so this one tells you that it was being deposited based on the characteristics, based on the way that it is, in fact, graded is what we like to say. So if it's coarse grained at the bottom and fine grained at the top, that's a graded bed. In fact, so it's a massively graded bed in this case, probably a result of some of those flash floods, or maybe a result of mass wasting events where you get debris flows that are bringing out the boulders and so forth out of the canyons. And so these would be interpreted. And we like to make a distinction here. This is pretty important in science. We can describe those rocks. We can describe the grain size. We can describe the sorting. We can describe that it's graded. And so the sorting is very poor here. You can tell that, right? Because there are large grains, and then there are some grains that you can't see with the naked eye, right? So there are even clay-sized grains in that deposit. So, we can describe all those characteristics. Those are the observations. From those observations, and based on the modern analogs that we know and understand that we've studied in places around the world, we know that that is very similar to what we would see. You would say it's comparable to an alluvial fan. And so we make an interpretation. So the rock knows where it came from. The rock accumulated wherever it did, right? It tells a story, though. And so we get to translate that story. And so from the observations, it leads us to draw an interpretation or a conclusion about what we think that rock is. And so that is interpreted as an alluvial fan deposit right here. Oh, that's from near Globe, Arizona. So it's a little bit, it's close to the Salt River Canyon, I think it is. So, rocks are everywhere, So it's like, you wouldn't believe it, but there's conglomerates right here in Missouri. A fair number of them, in fact. And so there are things that we study even here that don't look exactly like that, but not too far off from it. Maybe not quite so massive of boulders. We don't have that high of mountains here, right? But here, an alluvial fan. So here's where we look at it. And so what is an analog? An analog is a modern example of something we can go out and study, and then we can compare ancient rocks to that. And so this is a modern, we say modern, it's a recent alluvial fan right here. And this is out in Death Valley in California. And so this is one of the lowest elevations in North America right here. It's 220 some feet below sea level, I think. And a giant mountain valley. And so there's a mountain on one side, there's a mountain on the other, and in between there's this really low spot right here because it's all been uplifted, right? But really low nonetheless. Here you have a canyon that feeds out into that big valley. Well, it's a lake valley. So where the lake deposits all down here around the bottom. And what you see is the alluvial fan. So these sediments have a tendency to try to fan out across that landscape then. And the reason they do that is because they'll pile up on one side and it forces the flow out the other way. And so that's one of the common characteristics. And so very commonly when you have detrital sedimentary rocks, they'll form a fan shape like that. That happens in deltas. It happens in alluvial fans. It happens at submarine canyons as well. So submarine canyons tend to have a fan as well. And so the processes are not all that dissimilar between some of these, except the environment of deposition is very dissimilar. In this case, we're talking about arid. We're talking about, there's no trees in this image right here, right? And it's one of the hottest places in North America. But that alluvial fan is spread out across that landscape. And so you don't see things like root casts and things, other sorts of features in the sediments that are here. Eventually, that may become a rock if it's not eroded at some point, and it'll become a rock. It'll become a conglomerate. And so that's what you get when you have an alluvial fan right there. So alluvial fan is an environment of deposition. Alluvial fans are what we like to regard as a geomorphic feature. In other words, it has a shape. It has a certain place where they tend to accumulate. You don't find too many alluvial fans. You may find, well, not too many anyway, in Missouri, right? So there are some perhaps, but not very many, because we have a tendency to get a lot of rain here and it washes most of that material on down, but we don't have the same grain sizes usually. So in this case, that environment of deposition is called an alluvial fan. Now you see these things around the world. You see them in China. You see them in Mongolia. Any mountainous region is going to have alluvial fans, especially those that are near deserts like this. And so that's a modern alluvial fan, or a recent alluvial fan in Death Valley right here. We study things like this in order to understand what the ancient rocks would look like. Well, why are the ancient rocks important if they're alluvial fan sediments? Well, it's part of Earth's history. We try to understand Earth's history because these sort of processes, because maybe we find some rocks that you could interpret as an alluvial fan, but there's no mountains there anymore. Well, the mountains may have been eroded away. That happens much more commonly than what you might think. It doesn't take forever to erode mountains, apparently. Millions of years, perhaps. Just not even tens of millions of years at the very most, I would say, in some cases. So here we have an alluvial fan. I'm going to take you on a little, I'll take you to the beach here next. Here we are this is a place near Santa Cruz, California. This is in Monterey Bay. And here you can see the sand down here at the bottom. And many of you, I'm sure that almost all of you have experience with sandy beaches like this. And so this is one of the places where they built a pier out there. They had a ship out there that was made out of concrete. The concrete broke and the ship is still there. But this is it's a place where people go to fish and so forth. But this is a place where the sand accumulates, right? And so in the summertime, the sand builds out real nice wide beaches. In the wintertime, the big waves come in and they wash all the sand offshore. And so it's kind of a neat sort of setting here, but the particle size, sand grains. Well, why don't you find any muds there? Because it's too energetic. Because the muds would get washed out farther offshore, where they're never going to be washed back in by the waves, because it's too agitated in the wave sort of driven environment for the shales or for the clay particles to settle out and form a shale eventually. So here you can see another shot of a beach here. This is Hidden Beach near Santa Cruz as well. This is a little bit south of Santa Cruz, and on the distance back there, above Monterey Bay here, you can see the peninsula that forms where Monterey is. So, what's the name of it? Carmel by the Sea is on the other side of that peninsula. So those are mountains down there, right? So this is where the sand comes from, mostly from the Salinas River, and then it gets washed along shore here. And so each one of these, in fact, gives us a little bit more information. So the slide previous to this, you saw all the footprints that were there underneath the boardwalk, underneath the pier. And here you can see footprints walking along the beach, maybe some kelp. Kelp is a marine plant, right? So if you would actually preserve the cast of that kelp, it would give you a clue as how to interpret that depositional environments. What if you found bird tracks? What if you found, ripples and things like that? Well, those are all indications of the depositional environment. And in fact, most beaches actually slope towards the ocean, of course, as well. And so the bedding is also an indicator of how we would interpret a depositional environment. So these things that we see here, some of these are called trace fossils, like the footprints or the bird tracks. And so if you had a cast off of some of those plants that may have washed on shore here. Those things also would be a type of fossil as well. But the sedimentary structures may include things like, well, if you had a bubble, right, that was incorporated into that sand as well. You turn it into a rock eventually, and you may find that there are enough clues to be able to help you interpret that as a beach environment, which in this case, this is obviously beach here. But again, that's a geomorphic feature. We're talking about waiting tens of millions of years for this thing to become a solid rock. Well, how does that happen? Those grains could become cemented together through natural processes, lithification, we call it, forming a rock. And then also it's either cement or in fact, these things may be washed away. It is California after all, right? What do other environments look like? Well, here's some ancient rocks right here that would date back probably 15 million years, something like that. I think they're Eocene here, in fact. This is a very famous surf spot right here. It's called Steamer Lane. People ride shortboards here for the most part. And so this was this was a winter storm that was blowing up these huge waves here. And so you didn't see any surfers out that day because the water's just too turbulent. And you could easily drown in a surf that's that high. In this case, the rocks that you see, that's not sediment down here in front of this guardrail. That's actually a point of land there, but it's land that has some ice plant growing on it, which is like a succulent plant that lives in sandy conditions like this, and it's very salt tolerant. And there's a little tiny bit of sand over the top of the rock here, but the rock itself is made out of sand. That's our ancient sandstone that accumulated on a beach, and today it is being weathered away by the waves that hit that point and knocking those sand grains loose with every wave that comes in these huge winter storms that come in. It erodes a little bit more of that sand, and that sand winds up where? Well, downstream, down the beach. And so it gets carried by the currents down that way. And so the currents would take this material, move it along past Santa Cruz, and then on down to places like Hidden Valley, or Hidden Beach. So here you can see some people watching the waves because it's just amazing when these huge storms come in. I used to live in Santa Cruz here, so it's an amazing sort of place. When I was living in Santa Cruz, I got to go to places like this. So this is a geology stop I got to go to. I was working with the U.S. Geological Survey, and this is the west end of Molokai. It's like desolate out there. There's no houses, nobody's out there. And yet there's all these really cool rocks here. And so what you see here is another type of sandstone. And you can see some cross-bedding in this. And so cross-bedding is this idea that you can have those sort of like dipping beds, like going into an ocean, right? And they're all dipping the same direction. So that is a type of sand right here that would be interpreted as an ancient beach. A little bit more high-energy beach than what you saw in, for instance, at the Concrete Ship or at Hidden Beach, but still a beach nonetheless. And so this is the west end of Molokai in Hawaii here. Other depositional environments. If you're out in the deserts and you have already seen like the alluvial fans and so forth, in this image you can actually see a type of alluvial fan, a very small one up against the rocks over here. Those are actually sandstone in the distance there, the white rocks over there. But the rock right in front of you is silt. And it has a little bit of clay in it as well. And it forms this sort of like flat plan like this. It's like a pan, if you will. And that sort of like flat surface right there, it gets water. Believe it or not, it rains in the desert. And this thing can be filled with water, like 3 or 4 inches of water. It never gets very high. The silt gets wind blown in because it's a very dusty sort of place. And so that silt accumulates in these sort of lake basins like this, where they call these things playa lakes. And so playa is the Spanish word, of course, for beach. And so this is a Playa Lake deposit right here. And this is out in western Utah right here in Ghetto Playa. But this thing is so flat. You can go 90 miles an hour across I've done this before. You can drive 90 miles an hour across that flat surface right here and take your hands off the steering wheel because it's that flat. Unless you got really bad steering or whatever. You have to be careful when you do that, right? So I don't encourage people to do that because they cut some trenches through there to get people to slow down. And it was pretty effective at doing that. But here you are looking at another sort of depositional system here that is a lake deposit. It's a lake deposit. It's very fine grain. It's not like river channels that would have lots of sand or maybe some gravels in them, right? So this is a very fine sort of depositional environment right here, a lake deposit, a Playa Lake. Other sorts of places. In central Utah, there's this, if you leave eastern Utah, let me put it this way, away from Moab, most people go to Moab for vacations to see the arches and also to see canyonlands. And then as you're driving west towards the interstate, this is Interstate 70 right here, and it truncates into Interstate 15, I think it is. This gap right here that you can see where the highway's going up that canyon right there, that's called the San Rafael Swell. It's an area that was uplifted, and the canyon then cut down into it. And then much, much later, of course, they built the highway through there, 4 lanes, a road that went through there. But the rock that they went through right here and the rock that was cut through by that canyon are sandstones as well. So that's a quartz sandstone right there. It's a pretty fine-grained sandstone, not super fine, not very fine, but it is a fine sandstone. And what you find when you look at these rocks, in fact, very commonly, they're cross-bedded as well, except it's not cross-bedded from beach processes, which would be waves washing on shore and then dragging some of the sand back with it, leaving these nice flat surfaces or ripples if you have a little bit of a current in it. In this case, you're looking at deposits of sand that accumulated in sand dunes. And so wind-blown processes are responsible for this. There are certain things that we look for when we look at wind-blown sediments. And so that's the interpretation for this. And it's just absolutely massive, too. And so you don't see any of the sort of features that you would see along a beach, for instance. So you don't get marine fossils. You don't have any of that sort of material in there. In fact, what they do find is below the sand here, they even find some dinosaurs in some of the lower rocks that are finer grain. We're going to move on a little bit faster. I'm going to try to go a little bit faster here, but this is the sort of stuff that I do for a living, right? So this is what I really enjoy. So if I talk too much, I'm sorry, but that's just the way it is here. You're a captive audience, but I don't want to take advantage of that either. So what you see here in the next photograph is another canyon where it's cut through a limestone in this case and a shale down below it. So the shale forms a slope. The limestone forms the cliffs up at the top of this image. So each of these rocks, in fact, has a name. In fact, so what you're looking at there is the Pio Shale. And then at the very top up there, that is the Howell limestone. And so at the very top, you get the Dome limestone, I think it is. And so here you have these beds that accumulate in shallow ocean waters. Okay, well, shale, as we talked about already, is below normal wave base. At the very top of that shale, you can actually see some fine grain sort of cross-bedding and a few carbonates in it. So carbonates, now that's another sort of story now. So all of a sudden, carbonates are not detrital rocks like the shale is. So the carbonates, in fact, are useful for determining ancient climates as well. They would have formed in ancient oceans, but we're out of the realm of detrital rocks generally when we talk about limestones. So a limestone's made out of calcite, and calcite is CaCO3. And so, in fact, these generally happen, or they're usually accumulate in shallow marine waters that are in a tropical setting, somewhere between 30 degrees north and 30 degrees south latitude. Today, anyway, that's where they accumulate. So places like the Bahamas, places like the Persian Gulf, and some other coastal areas where you get some carbonates like this, around the Caribbean and so forth. But it's not a detrital sedimentary rock in this case. It is a chemical sedimentary rock because it was deposited from the precipitation of that calcite. So that is an accumulation of calcite mud, essentially, when you look at the upper cliffs here. Very shallow water, so maybe 30 feet, 50 feet at the very most water depth. For the shales down below, well, they weren't carbonate, right? And so that would have been derived from land sediments. And so we like to say that they are, if they're derived from land, we call them terrigenous, or, terra means land. And genus means the origin of, right? So origin from the land is terrigen. They're terrigenous sediments. And so these accumulated close to a continental shelf. In fact, probably on a continental shelf here. So we look at all these sort of things, and so we get clues from the rocks in order to make our interpretations. And just to show you what it looks like, where modern carbonates are accumulating, that's our analog for this. So that and the Persian Gulf are two of our leading analogs that we have for carbonate sedimentary rocks, the chemical sedimentary rocks. And if you look at the Bahamas here, there's some deep water settings. There's some very shallow water settings as well. So carbonates have this tendency to be right near sea level where they accumulate. So typically not very deep water, although they can be deep. Okay, so, and that's Cuba down to the south here, and that's Florida off to the west edge, okay, of this image here. So Nassau is, as I recall, it's like, that's called Tongue of the Ocean. Eczema Sound is over on the other side over here. So the big island on the Bahamas here, that's Andros Island. So yeah, carbonates there. And in between Florida and Cuba and the Bahamas there, that's the Casal Bank right there. So again, carbonates that are accumulating in very, very shallow water. Just absolutely beautiful, aren't they? It was like that beautiful turquoise blue. So what do those rocks look like after you turn them from sediment, which accumulates in a tropical place, which is usually a kind of white, muddy material? When it gets deposited, it eventually goes through a whole bunch of different processes. That it gets buried first, and then after that burial, sometimes there may be some organic matter in there. And if you bury it deeply enough, that organic material becomes cooked a little bit. And so this is a dark gray limestone right here with some little tiny algal accumulations, algal clasts, if you will, or grains. They're actually called oncoids. We just sent a spacecraft to Mars to try to find things like this. Those are oncoids. They're made out of cyanobacteria, so one of the most primitive sort of life forms on this planet. We think that we can maybe find something like that on Mars. So these things are layers and layers of that sort of, it's like pond scum essentially, right? So it grows layer after layer, but accumulates and becomes turned into a carbonate. It's relatively hard surface when these things, they photosynthesize. And so when they photosynthesize, it pumps out the carbon dioxide and it precipitates the calcite here. So the gray areas in between, you get some other carbonate muds in there that accumulate. And so, but that is a depositional environment. It's going to be relatively shallow water. It's going to be something that's raked by waves that rolls these little algal balls around. But that, again, is from the same canyon, actually. So that is up in that's actually in the Howell limestone right here. So that is pretty cool. So that's a type of limestone right there. We call it, in the business, we call that an oncoid grainstone. But you can just call it a limestone, because how are you going to recognize it? Well, you're going to drop dilute hydrochloric acid on that, and it will fizz. And so you'll say, well, it must be made out of calcite then, or dolomite. And in this case, it's all calcite. And that's how we identify it. Here's the bottom rock there then. This is that one that forms that slope. That's the P.O. Shale right here. And you can see how it forms these flat layers like this. They're made out of clay grains. These clay grains would have accumulated in relatively deep water, at least low energy water. And so the grains would have settled out. And then eventually, as other rocks were piled on top and they became more deeply buried, it squeezes the water out first, and then slowly it's going to harden and compact those rocks. And so that rock, in fact, was probably 4 or 5 times thicker, and it just got squeezed and turned into what we today know as a shale. So shale, like this one, this is a green shale right here with a little bit of iron staining in it that gives it that sort of orangish color in here as well. That shale, in fact, has been compacted substantially, and then it's almost been buried so deeply that it is metamorphosed. It's a very hard shale. It's a harder shale than most shales that I've seen before. And so this is at Margam Canyon again, and this is the P.O. Shale right here, but made out of clay grains. It's so fine, in fact, you can't see them, right? So you have to have a hand lens, and even then, you wouldn't be able to see it. Okay, now we've talked a little bit about silt, right? And now we've talked about the clay particles. So these are detrital. The silt was detrital when we were back at Ghetto Playa. How do you tell the difference between silt and clay? This is a geologic trick, okay? And actually I've seen it pop up on the internet before. Did you know that geologists eat rocks? Well, yeah, we do actually. So what we do with a shale like this to find out if it has any silt in it, we'll take a little tiny bit and nibble at it. And when you nibble at it, you can actually detect with your teeth, very sensitive, to be able to tell if it has any silt in it, because silt grains are larger, especially if they're made out of well, they're going to be hard too, right? They're going to be made out of quartz. So quartz silt is going to scratch your teeth a little bit. And so, but the clay will not. Clay is like smooth, right? So the grains are so small, in fact, they won't scratch. And so soft, in fact, that they won't scratch either. So that's one of the things that we do. We taste rocks and we try to grind them up against our teeth to figure out what they're made out of. Does it have silt or not? That's the question we ask. Still in Margam Canyon here, I'm going to take you up the canyon here, and we're driving through this. The canyon makes it all the way to the other side of the mountains there. It's like a gap in between, right? So at Margam Canyon, you get this sort of deposit here. This is really kind of cool. As you're driving up the canyon, there's these red stained blotches here and there along the walls of that canyon. And when you look at it, it's made out of all these other kinds of rocks that are in there. And so here you've got limestone clasts in here, hammer for scale there. You get blocks of other material, and then you get this sort of reddish clay in there as well. And so what you see here, in fact, you would call that a conglomerate. You might call it a breccia in places, but it's mostly a conglomerate. Most of the sharp angles have been knocked off. And so I would call that a conglomerate right there. And so again, the grain sizes, it's a detrital sedimentary rock, right? So it has to be if it's a conglomerate, right? Well, it doesn't have to be, but usually they are. And so it has grains that are classed, I should say, that are gravel size all the way up to boulder size. And then in between in the interstitial material, that is what we call the matrix. That matrix, in fact, is very poorly sorted, and it has sand grains in it, it has clay grains in it, so very poorly sorted. And you could say that it's like, well, that must be some sort of like an alluvial fan, right? We're in the mountains, right? Except when you look at these rocks and you see them where they're distributed, they're in these round sort of features as you're driving up the canyon. There's no context for them being part of a larger alluvial fan. And in fact, what you see is also embedded around this some calcite cements very commonly. And in fact, this would be interpreted as an ancient cave fill. So this is actually what people refer to as Paleocarst. And so we're going to look at Paleocarst a little bit later in the semester here, or at least karst later on the semester when we talk about caves and groundwater. But in this case, this would have been a limestone bluff that had a cave etched out of it, and that eventually this material got funneled into that cave and deposited there. And so here you can see some of these grains that would have collapsed into that cave or been washed into that cave perhaps. So a conglomerate in Margam Canyon. Here we're a little bit south, and these are the same white rocks that we were looking at before in Ghetto Playa. So this is right at the edge of Ghetto Playa here. And in fact, we're standing on what is a very gentle alluvial fan here. It's a very fine-grained fan, in fact. But in fact, it's not where the major part of the river or anything like that flows through, or it's not really even a river. The canyon snakes around the back of these mountains, in fact. But the rock that you're looking at here in the foreground, that is a sandstone. And in fact, it's so hard, and this stuff has been so deeply buried, it is right on the verge of being a a metamorphic rock because pressure and heat can turn sedimentary rocks into metamorphic rocks. It's called the Eureka Quartzite here, but that's mostly because of how hard it is, not because it has grains that have been mushed into one another. So that is the Eureka Quartzite here. It's really a sandstone. It's a quartz sandstone, but it's a very hard. It is so hard, in fact, that Native Americans used it for projectile points. They'll actually take an edge and break in that way. Above that, in fact, those are dolomites, and so that is a dolomite, another carbonate unit that's above that sandstone here. So when we look at these rocks, one of the things that we do is we try to figure out, well, that's a detrital sedimentary, that's a chemical sedimentary rock overlying it there. What's the boundary between them look like? It would have been somewhere where sea level was rising, right? And so if this is more like and there's pretty good evidence that parts of the upper part of that sandstone anyway were beach deposits. Above that, in fact, you get these carbonate muds, which would have been slightly quieter water, but still shallow marine waters. So they find trace fossils in the upper part of that shale, the upper part of that sandstone, that tells us that there were burrows that were vertical burrows, just like in modern settings where clams and things like that will extend themselves out at high tide, and then at low tide they'll draw back into their burrows in order to protect themselves. And so that is a marine succession right here. So that is the Eureka Quartzite, and I think that's the Ely Springs dolomite above it there. We're going to look at some more depositional environments here. This is kind of neat right here. This is actually a granite that's down at the bottom down here, but it's overlain by a shale in this case. And so there's actually some sandstone beds in there as well. And some of them are pretty dark gray, right? So some of the shale beds are gray and some of the sandstones are gray here. But there is a surface right there that is where the granite itself was weathered. And then over the top of it was deposited this shale in shallow marine setting. Now, how do we know that? Okay, how do we know that granite didn't intrude into these rocks? Well, if it had, it would have baked those rocks. I mean, it would have been very irregular, and you could actually see where it would have hardened those rocks from all the heat and everything, but those rocks aren't all that hard. They're pretty soft here. This is in the western part of the Rockies out here. This is pretty close to Grand Junction in that area of Colorado. So that surface right there, that is an igneous rock that's overlain by a sedimentary rock, in this case shale and sandstone. That's regarded as a nonconformity. And we're going to come to nonconformities next after sedimentary rocks here. So we're going to talk about some of the key geologic principles. And nonconformity is one of the ones you want to tuck away, because anytime you have an igneous rock that's overlain by sedimentary rock, that's going to be regarded as a nonconformity. That is, if it's not an intrusion of some sort, right? If it was an intrusion, we'd call it a pluton down below, and then we would have, that would be the country rock that got intruded into it, but that's not the case here. In this case, there was erosion and then deposition of the shales and sandstone above it here. Okay. So when it comes down to the detrital sedimentary rocks, you've seen examples of shale from these slides. You've seen sands. You've seen silt. You've seen some of the different grain sizes that we've illustrated. So these are only 5 of the rocks that you have to know right here. So breccias, you know what a breccia is, has angular class, right? So class means that it's larger than 2 millimeters, and you have to have a fair number of them in there in order to regard it as a breccia. So if you got a lot of angular class that are larger than 2 millimeters, that's going to be a breccia. If they're rounded class, you're going to call it a conglomerate. So if the class, again, over 2 millimeters, right? That's the cutoff. Even if it's surrounded by sand, even if it looks like a sandstone that's surrounding those large clasts, if you have enough of those clasts in there, we're going to call it a conglomerate with a sandstone matrix. So the matrix is the material that fills in between the clasts. Arkose is the next one. So in that last image there, what you don't see is when you get up close at the very top surface of that granite, there's some arkose in there. And what an arkose is, we like to call it a sandstone that is derived from a granite. And so arkose tends to have a lot of feldspars in it. And so if you find potassium feldspar grains in a sandstone, that's going to be called an arkose. It's kind of an immature rock because, as you know, feldspars eventually will become clays. But in this case, they get incorporated into a rock before they have a chance to weather and become that clay. We're going to call those an arkose. Quartz sandstone, pretty easy. Quartz sandstone is going to be made out of quartz grains. What size? Well, 2 millimeters or smaller, right? All the way down to very fine sort of stuff that you would find. It's going to feel like sandpaper, right? And so that's what you have for quartz sandstone, made exclusively out of quartz grains. We usually use a hand lens when we look at these rocks in the field. And so with a hand lens, you can get right in there and see what binds the quartz grains together. That's pretty important for us as geologists. For you, not so important, right? But for, if you're going to become a geologist, yeah, probably important. So you'll want to get a hand lens at some point. Quartz sandstone is easy to see. There are clues that we see even in the grains, right? And so some of the grains may, in fact, have a frosting around the outside. And if you're familiar with like etching, one of the ways that you can etch glass, in fact, is to sandblast it. And so that's what these grains are. They've been sandblasted. Well, they are sand, right? And so if they're windblown and don't have the water to kind of stop the collisions of the grains, they can become pitted and the surface can become kind of roughened like that. So we call them frosted grains. And so frosted grains is an indication that these sort of sand grains may have been transported by the wind at some point. So that's our quartz sandstone. A greywacke is kind of wild because a greywacke actually typically includes some not just quartz sand grains, but maybe some feldspar grains and some other grains in there, but also some clay grains. And so it's like a dirty sandstone. Well, how can you get a dirty sandstone? Because wouldn't the clay go one way and be deposited in deeper water, and then in other places the sand would wind up, let's say, in a beach if it's a marine rock, right? Yes, that's right. But sometimes the quartz sand can actually slump or get moved down slope into the deep oceans, perhaps. And in that case, it's like a submarine deposit. And so greywackes are a type of sandstone that very commonly is in relatively deep water for sand. So it's not one that's a beach accumulation. It's a deep water sandstone typically. And it's where you have all of the grains mixed together. Typically, those grains will get sorted out by beach processes. Waves will do that, and whether they're being washed on shore, or currents can sometimes do that as well. So currents can also wash the clays out and deposit the clays farther out. But in a greywacke, they've been mixed together. And so lastly, shale. Shale and claystone actually is another one too that we didn't mention here, but claystone doesn't have the layers that shale has. So shale is noted from its plate-like appearance, as you saw with the PO shale. And so those plates, in fact, have a property, we call it fissility, Fissility. Fissility means that you can break it or you can peel it apart, essentially, kind of like mica, right? Mica doesn't have fissility, but those plates are a type of cleavage, right? Well, in this case, we're talking about a rock cleavage, if you will, and you can pry those layers of shale apart from one another. And so fissility, shale has that sort of quality to it. And so that's what makes it different from claystones. And so claystones can be usually just clays also. Now you can take claystone and try to figure out if it has any silt in it or not. You can take a shale and try to figure out if it has any silt in it as well. Do any of those react with dilute hydrochloric acid? They will if they have carbonate clasts in them, right? So a conglomerate or a breccia potentially can fizz and trick you into thinking it's a limestone, but that's just what the clast is. As it turns out, the very last rock that is formed is the rock that we try to identify. And so even if it has limestone clasts in it, it may be a conglomerate. Okay, so a conglomerate we still regard as a detrital sedimentary rock because they've been moved by currents or some sort of flow-like characteristics that would have caused it to accumulate in a certain depositional environment. So that is our detrital sedimentary rocks. Here's some views of it here. You can see a breccia with the angular clast in the lower left here. In the lower and the middle part there, you can see that the grains have been rounded more, but it has a sandstone matrix. And so those are, that's a conglomerate right there. You can see interbedded sandstone and shale actually over here on the upper right. I don't know if you have a piece of that or not in yours, but the clays actually kind of drape over the sands there, but you can see ripples in it. So that's a sedimentary structure right there. It's mostly sand grains, though, because you can actually see the little tiny layers as they go up and down and up and down, and those are ripples. Now, in the upper left-hand side, that is the sandstone there. That's a quartz sandstone. Now, it has a little bit of orange to it, and the reason for that is because when iron grains get into sandstone like this, they will very commonly be exposed to water at some point, and they will rust. And so that's what you have with the iron staining in that rock. But it's mostly sandstone. And if you felt it, you would feel the sandy nature of that rock. We're going to go on to some more types of rock here. Coal, we're going to go into in a little bit more detail later on here, but these are what we regard as an organic sedimentary rock. At least that one is on here. That organic sedimentary rock is made out of compressed plant debris. And so you can compress the plant debris, and eventually it's going to become nothing but carbon. Carbon is the number one ingredient for coal then. You talked about the one in the upper right-hand side. We kind of talked about that a little bit already about what chert is. Chert is cryptocrystalline quartz, we like to say. I think we talked about it a little bit. Native Americans made arrowheads out of it. It has conchoidal fracture. It's very hard. It has a hardness of 7, same as quartz, right? Whereas the middle one in there, you can tell that it's not quartz because you can try it on a streak plate or any other sort of setting, and it's so soft, in fact, you can scratch it with your fingernail. So it's gypsum. It's rock gypsum, I guess is what you're going to call it in your labs, but in fact, it's gypsum. It's made out of the mineral gypsum. But also, actually, the brown layers in there, those are actually made out of dolomite, as it turns out, which is also a type of rock that would have accumulated in the same sort of depositional setting as the gypsum. It would have been an evaporative sort of setting in a desert. And in this case, it would have been flooded with ocean water, which is salty. The water evaporates in a very arid climate, and then you precipitate the gypsum crystals, either a selenite or some type of fibrous, right? You remember the other variety, the sparry variety of gypsum as well. And then also you've got the satin spar, and then you've also got the layers of gypsum, layers of dolomite that separate those layers of gypsum. Okay, so those are the three of the, one organic at the upper left here, and 2 chemical sedimentary rocks. I mean, we talked about chert being equivalent of like petrified limestone, if you will. In this case, what you're really looking at here is fossil seafloor that has had a lot of silica flow through it, and it replaced the limestone that was there. The other 2 are simply limestone, and this is where it gets into that sort of gray area, okay? On the left-hand side, that limestone is actually a detrital rock, and we've talked about this just briefly already. That's an ooid grainstone right there. It's made out of ooids. Ooids are little tiny particles that would have accumulated in shallow oceans in places like the Bahamas. And I think I maybe mentioned to you once before, but on the west side of town, there's a place that has an accumulation of ooids as well. And in that place, it is the Short Creek oolite. Okay, it's one of the local rocks that we have around here, Mississippian in age. So 330 million year old rocks, but in fact, they're made out of calcite, and they would have accumulated in a shallow ocean where waves would have agitated that material. On the right-hand side, that's the most common rock in southwestern Missouri, well, at least this area of southwestern Missouri. That is a limestone right there, and it's made out of crinoids, so it's made out of fossil material right there. And that's the Burlington Keokuk limestone there, in fact. And so that's the name for it. It's named for the town of Burlington, Iowa, and the town of Keokuk, Iowa. And just because in this area we can't recognize the difference between the two, we know that the Burlington is the lower part of this rock unit. We know that the Keokuk is the upper part of that rock unit. So that is what we have here. That's a limestone that was from that local quarry around here, or local outcrop of some sort. So those are 5 of the organic and chemical sedimentary rocks. In fact, one of them is, you could argue, is detrital. One of them is certainly organic, that's the coal. And then the other 3 are, precipitates of, in an evaporative sort of setting. The other one is a groundwater sort of based, replacement with silica. And then the limestone would have accumulated as organic material as well in the form of fossil debris. And so these are living creatures that make their skeletons out of calcite, right? And so when they make their skeletons, when they live, they die, those skeletons fall apart, and then they accumulate and form this limestone. And so, in fact, that's an organic sedimentary rock as well. So the coal in the upper left and the limestone in the lower right, those are the two that are organic in this. There's a detrital limestone here. There's an evaporite, which is a chemical sedimentary rock, and then a chert, which is also a chemical sedimentary rock here. Now, I'm going to stop right there, and we're going to come back to this in just a minute here. But because we got a lot of material to go through, this is sedimentary rocks, and you're getting a lot of it, okay? So this is a little bit deeper detail, but I've reached kind of my time limit here. This is at least 1 hour that I've got here. So we're going to talk about how sediments can become rocks next. And so we're going to talk about cement and lithification processes and compaction just a little bit, but we're going to talk a little bit more then beyond that about other sort of depositional environments as well. So I'm going to leave you with that right now. So we'll get on with the sedimentary rocks. Thanks for your attention. Yep. Bye now.